We already got a very nice introduction from Dr. Chung, so I'm not going to go too deep into all of this. But really, what the DARPA challenge meant in terms of research, it was really pushing the cutting edge. So when the challenge was announced, there were really no complete solutions that we could just have taken and put into a system, make it robust, and do anything close to what all teams produced in the end. So it was really an exciting challenge for robotics and an opportunity to push the frontier in research and also see how well we can actually apply research in real-world applications. Now, Team Cerberus, what does it mean? Of course, Cerberus is in Greek mythology, the three-headed dog that guards the underground. But we also managed to make an acronym out of it. So in the end, what this means is we imagined from the beginning a cooperative team of robots, both legged and aerial systems, which have complementary strengths. And we knew from the beginning that we need to focus on robust localization and mapping, because there will be perceptual degradation down there in all forms, just challenging environments, and then also artificial hindrances and obscurants that DARPA prepared for us. Of course, we need resilient autonomy down there because communications will be either not available at all or highly degraded. And then autonomy is necessary because no operator could control all these robots. And then the team was very multinational, so and even intercontinental. So it was led by the Autonomous Robot Labs, which at the time was University of Reno, and now moved to Norway to NTNU. We are from ETH Zurich, and there are other academic partners from Berkeley and Oxford, and also industry partners from Flyability and SNC. This is the environment of DARPA during the finals. So we had one single entry, and then we had these branching things that went into the individual subdomains. Of course, we didn't have access to all this very nice point cloud data beforehand, but that kind of gives you an overview of what this environment looks like and really how diverse the entire terrain down there was. And it's not only diverse terrain, but there's also just challenges in terms of fog obscurance and then dust being blown up when flying around. So it really was challenging to navigate down there, and we imagined a unified approach to address all of this challenging. So this is kind of an overview of the individual components that make up our team and our entry. We had a very versatile team of robots. So we had our Dexterous leg robots, the animal robots, and then also flying robots that were able to go to all the places that ground robots cannot, and supplement these ground robots very well. Of course, the platforms themselves don't do much unless you have resilient perception, because we know it's very challenging. You have many things that can make your senses break. We imagined multimodal sensor fusion from the beginning for localization and mapping. And then, of course, once you do have perception, you also need to act autonomously, because we had a team of robots. So there's, even if there was an operator who had control over the robots, there's no way that he or she could control all of them at once. And then also there was highly degraded communication, so there was no way, even if we had some kind of superhuman to control it. Then also, because we had a single operator, the robots themselves needed to do the artifact detection. So there's no way we can stream all this image data back to the base station, and then also the operator has better things to do than look at image streams all day and click at things. And then, of course, because it's an underground environment, we had no real communications available on there. Of course, the robots could have gone in, collected everything, and come back out, but that's highly inefficient. So we also need to take care of networking. So we went to a mesh networking solution to get communication and have the robots be able to communicate back some information when they're inside. And then, of course, at the core of everything was the human-robot teaming, because in the end, we want to have the robots enhance the human capabilities and still have the human do all the inject some high-level knowledge and intuition into the system, and really be the core that controls everything. Now, getting into the systems that we had our animal sea-legged robots that we highly customized for the task. We had two different specifications. One that was more geared towards exploration, and then a supporting configuration that was tasked to establish network communication down there. We had a variety of flying platforms, both more traditional ones. We had collision-tolerant drones, as well as a tilt-copter drone that could adjust its posture. And we had a communication extender wheeled robot, which basically functioned as a mobile antenna with a very long cable that would just remote controlled for the first couple meters, just so we have a better communication inside. But it was also capable of detecting artifacts, although that didn't come into play at the end. Moving forward to our legged robots. Again, as I mentioned, we heavily customized with a whole bunch of sensors on top. We used a commercial inspection head from Robotics, which is a pan-tilt unit with a zoom RGB camera, as well as a thermal imager and a spotlight, so you can actually see down there in the pitch dark. This was only tasked for artifact detection, but we also had a multi-camera set up in front of the robot, which we both used for artifact detection, also visual odometry and visual snap. So we had cameras facing in all directions, left, right, forward, up, and we had the pan tilt unit. So we really were able basically in all directions to detect the artifacts. Then we had LiDAR for doing SLAM and localization. And we had dome LiDARs in the front and in the back of the robot, which basically mostly were used for terrain mapping for locomotion and navigation. And yeah, this complementary sensor suite was important in this environment. We have lots of challenging things going on for perception. Then this platform by itself doesn't do much unless you control it. And as we heard earlier from Takahiro, we used reinforcement learning-based perceptive locomotion, which was very capable of moving swiftly in these challenging environments, but also was very robust against all the challenging conditions that were going on down there, because the net frequently breaks due to various factors. But the robot never fell and worked the entire time and was able to overcome any obstacles that were present in the environment. And we also had a navigation planner specifically for legged robots that enhanced the capabilities of the exploration planner. And this was specifically designed for legged robots. So there's a where the robot needs to be able to step somewhere. And also there's some learning-based components in there that were able to assess navigation risk, so that we're able to plan safe paths and fast paths at the same time. Now for drones, of course, it's also very important to make them resilient. Because basically with a regular drone, when you touch anything in the environment, you usually crash. So we focused on collision-tolerant drones that had a very nice airframe that was protected from collisions with the environment. The drone on the left, that's a colibri drone developed by the Autonomous Robots Lab. And then we also had a Gagarin drone from Flyability, which is a commercial drone for industrial inspection. Those were the smaller drones. And we also had a larger drone, which was a tilt-copter design, that had longer range, more endurance, and was able to carry more payload, and it was able to adapt its posture so that it could actually fit through narrow gaps in the environment. Moving on to perception. Of course, we're operating underground. There's no way you get any kind of GPS signal or anything like that. So yeah, GPS is out of the question, but then also the environment down there is very complicated. So every sensor will encounter something down there that will make it break. So it was very dark. No light at all, it's underground. There were obscurants injected into the environment by DARPA. There was a very self-similar environment, straight tunnels where LiDAR has trouble localizing with ICP or anything like that. And at the same time, you had very narrow parts of the environment, but at the same time, this was large scale. So it was really necessary to have multimodal perception to stay robust. Next slide. Yeah, so multimodal perception was crucial because you have complementary sensors that have different failure points, and if you combine them in a smart way, you can make sure that you always at least have some perception or localization, and nothing ever breaks, but you might have some degraded performance. So how we did this, we had a very flexible and hierarchical fusion approach, which we call complementary SLAM or CompSLAM. And how this works is at the core, the backbone is LiDAR SLAM based. And the LiDAR SLAM is fed by an odometry system on the drones. There was a visual inertial odometry. On the legged robots, there was a leg kinematic inertial odometry. And you had health checks at every level of this localization system, so that you could always fall back to the more robust system if you detected any failure at any point of the system, and ensure that you always have localization going in there, which was essential in autonomous operation out of communication range. Then that localization system ran on board each robot, so they did snap for themselves. But we also had a centralized mapping server, which created a map for all the robots. So every robot, when it was in communication range, sent back all its submaps. And then this mapping server combined them into a very big multi-robot post graph, which was constrained by the onboard odometry, by the visual features that the camera sent back, and also there was dense alignment between point clouds that it sent back. And that's a big optimization problem, gives you a very accurate map at the end for all the robots. For autonomy, we were based on a graph-based exploration planner. It was also presented here at ICRA and won the Outstanding Systems Paper Award, GD-Planner2. It is a graph-based sampling planner that tries to optimize for information gain and coordinates different exploration frontiers and decides which one of those is the most promising. And it also considers the mission time budget. So it is aware that in the DARPA challenge, we only had 1 hour mission time, and it made sure that it came back in time to still transmit all the data so that we can report in time before the 1 hour is over. And it's a hierarchical structure that this global exploration has in the local component, which tries to find a safe way towards the exploration frontier. And this system ran on both the drones and the legged robots. So it's the same planner running. And of course, they have different capabilities, so we had to make sure that for the legged robots, we stayed on the ground. So we had special considerations to navigate slopes, to have some kind of limit on the inclination, and also in the presence of negative obstacles, we actually allowed the planner to plan into free space, but we weren't even sure if there's something there or if there's a negative obstacle. Because we knew that we had the navigation planner to fall back on in case there is actually something unsafe there. And that actually happened on the subway station during the DARPA finals. So it was very nerve-wracking, but it was good to see that everything worked as intended. And then this is how this looks like for the drones. So this is footage from the urban circuit in the sets of the power plant in Washington. And yeah, the drone takes off, it starts planning, and then subsequently tries to go towards the frontier and explores around the core of this power plant. And going through fairly narrow gaps in terms of what drones can explore. And then when it reaches the end, it sees that it cannot explore any further. It automatically triggers a homing path, comes back to the operator to report back the map and the identifications of what it detected. And this also works, as I mentioned, on the legged robot. So this is footage from a deployment test and integration test that we did before going to the finals in the Hagerbach mine in Switzerland. So this is a 37-minute mission of the robot autonomously exploring, selecting different branches in this underground mine, to explore the entire environment and then come back to report all what it has found. Then, of course, we need to detect artifacts, both visually and non-visually. For the visual detections, we used YOLO version 3. And of course, there's no data set available in the environments that we were exploring with the types of objects that we needed to detect down there. So we collected our own data set, and in the end, we had over 40,000 images of our visual artifacts. And when collecting this data set, we made sure to have a realistic environment. So whenever we went testing underground, we usually also took data for object detection, also made actually trips simply just to different environments for object detection. And these ROS bags had various types of obscurance in there. We made sure to introduce motion blur because the robot will be moving during the mission and the images will not be very nice. It's also important to have diverse backgrounds. So the left image in the center, for example, that's a white band on a white background, very hard to see even for the human eye. And then also we use cameras with different resolutions because the flying machines as well as the legged robots had different cameras on board. Then when we detect these artifacts, we also need to localize them. What you do is you subdivide the detection bounding box. You do ray casting into the onboard volumetric map of the robot that gives you the position candidates for the artifacts, and then you average that over all detections in a certain radius, hoping that there's not two backpacks right next to one another, which luckily DARPA did not throw at us. And then for the non-visual artifacts, it's actually very similar. We had CO2 and Bluetooth detection on board. And there we also did a weighted average of the detection. So whenever the robot exceeded some kind of CO2 threshold or detected Bluetooth, we started accumulating position and did a weighted average based on signal strength to find the position of the gas or the Bluetooth artifact. So the final component of the technical solution was the communication infrastructure. We used a mesh network implementation, where every one of the ground robots actually functioned as a mesh of itself. So we could daisy chain basically the robots one follow the other, and we were able to pass on the information there. And also, two of the legged robots actually were Wi-Fi beacon carriers, you see it at the bottom left, that were able to drop Wi-Fi nodes. That's kind of cool that we could leverage the posture adaptation of the legged robots to actually drop these nodes. The drones themselves were not mesh nodes, but they could connect as Wi-Fi clients to this big mesh network. Then this is how this all looks like during the competition. So this is our animals going into the course. Again, just to make sure this is not footage we had while we were there. This is something that they provided to us afterwards. The robots all went in. We took about 12 minutes to send all of our robots in. So we were very well trained in getting all the robots out and in. And we sent them into different branches. Again, and that was an operator decision. So the high-level coordination between robots, that was done by the human operator, because we thought that the human operator has a better intuition of where artifacts might be and how the robots can best coordinate among themselves. And this is the outside view, but we also have a better indicator of what the robots themselves saw. So at the top, you can see the 4 cameras that we use for artifact detection in the front of the robot. So facing left, right, front, and also up, because some vents were actually at the ceiling. And then at the bottom, you can see the accumulated point cloud of the robot. The yellow path here is the exploration path, and then the coordinate axes at the bottom are from the animal navigation planner, which basically functioned like a very fancy path follower in this case. And then once all the robots went through the course, this is what the accumulated map looked like at the end. So you can see that we explored pretty far into the course, but actually not everything. So this big cave in the very back of the competition we did not reach, but we had very dense coverage up until that point. And Tim mentioned that earlier, that it was not only about going all the places, but also about actually finding the artifacts when you saw them. This gives an overview of what the robots were doing during the mission. The colored bars here mean that the robot was moving. The blue bars mean that the robot was in fully autonomous mode. The red lines mean that the robot was out of communication range. And you can see that most of the time the robots were actually operating in fully autonomous mode. Notable at the bottom, the animal 1, we lost out of communication range due to a dynamic obstacle. The robot never fell and was fully operational, but it just stood there waiting for a command, but it was unfortunately out of communication range, and no other robot reached it to establish communication until the very end, but luckily it was able to actually report all the artifacts it saw before we lost it outside of communication range. But other than that, all the robots were in communication to the very end and operational. And also the robot, the animal 1 here, was fully operational, it's just out of reach. This is a map of all the artifacts that we did detect. Was pretty well spread among all the animals because they all went into different branches. So we had nice spread among the different areas of the course. And the visual artifacts we mostly detected very accurately. And with the gas and Bluetooth accurate the artifacts, there's some variance in there because it's much harder to find the actual source because you basically accumulate just measurements while you're moving along. And this shows that actually our artifact detection system detected all the artifacts that we actually scored. So the human did not have to do any detection himself. He was basically just able to confirm the candidates that he saw as true artifacts, and they were automatically reported. And in the end, these 23 artifacts that we did score were enough to win the competition. We tied the points with CSI, Robotic was slightly faster. So then this brings me to the team that won the competition. Of course, that's not all the people that contributed to the competition over time. There's many people to thank, but I'm just going to thank Kostas Alexis, the team lead here, was basically the engine that's kept this train rolling over the entire all the years of the competition. And finally, that brings me to the lessons learned. For us, it was a good insight that we, from the beginning, went with a solution that we knew had the potential to be a very good solution with the legged and the aerial systems, even though in the beginning it was not mature enough to be in this really, really tough competition scenario. But it really paid off in the end when we had a very capable system, and also we believed that legged and flying systems were the correct solution in terms of hardware for this problem. And then in the end, we had a capable system that was able to overcome all the challenges we faced down there. It's very important to focus on perception and autonomy and the resilience and performance of both those systems, because when that's running, that makes basically everything else. It gives the operator more time to operate, to coordinate everything. He doesn't have to worry about individual robots, and you're just less prone to have loss of robots and all those things. We put a high focus on system reliability and readiness. That means a lot of testing. It's not something that researchers want to do maybe as much as we did, but in the end, it was very important. And then as part of that, it was very important to focus on also the human team training and readiness. Even if you're based in multiple countries and there's a pandemic going on, it's important that the people on the ground that actually deploy the systems are well-oiled machine. And then, of course, researchers always have new ideas and want to go further, but it's important that at some point you say, no, now it's enough. This is what we're going with, and we make this very robust and make this actually work during the competition. And that also gives you the opportunity to actually know the capabilities and limitations of the system, so that you can, during deployment, actually, you know what works and what doesn't work, and you're not surprised by anything. And of course, communication is very important. Even though the robots were fairly autonomous, it's always very important that the operator has some kind of insight into what's going on inside and coordinate between everything. Finally, we have a lot of open source code of what ran during the competition. So if you want to build on any of this or are curious about the methods, feel free to check all of this out. We also have robot models, so you can use the DARPA simulator to try and reproduce what we did during the challenge. And that brings me to the end of the presentation. I thank you for your attention, and I'm open to any questions.
Do we have any questions from the audience or from the chat?
Just from the chat. Okay. You can start with it. Please say it out loud.
So, first question. Judging from the types of terrains, a hybrid wheel-leg robot would perform better than a purely legged robot. There's plenty of semi-flat surfaces. Is this what you see as well? Yes, I agree. So the competition area that DARPA produced in the end was mostly flat. There was some very challenging things around, like railway tracks and some hoses on the ground. But in this particular course, a wheel-legged system would have been able to be much faster down there. But I don't believe that the speed of the robot was actually the limiting factor. We did explore quite a bit, and all the navigation and localization challenges actually, I think, were more limiting than just the simple speed of the robot. How close is the human supervision? Human supervision is mostly for critical decision-making points. Exactly right. So the human supervisor, of course, had the capability to give individual waypoints, but that actually never happened during the competition. So it was mostly about the human supervisor selecting which branch of the underground environment to explore. And not, that's basically the level of interaction that the human had with the robots. And then, of course, to accept the artifact candidates that the robots sent back. But that's more on the challenge side, not so much on the robot side.
I think you kind of half asked my question, but I guess I'll elaborate a bit further. So my question was going to be, I know you had humans in the loop, and if hypothetically the next challenge had no humans allowed and you had to just let them go 100% autonomously, what is the gap between the work required, do you think, from what's been done in the last challenge versus a hypothetical challenge without any humans in the loop at all?
So for our solution, it would be probably the robot coordination among each other. So the generalized mapping was centralized. So each robot mapped for themselves, but the combined map was centralized at the operator station. That can be optimized as long as the robots are in communication range. But then the higher level decision making, like one robot goes to the cave section, one goes into the urban, one goes to the tunnel. That was still up to the operator, and we had no decentralized decision making between the robots. That's the core autonomy part, I guess, that would enable a fully autonomous mission. And then the artifact detection. So when you tune the thresholds of what you consider an artifact, we were pretty lenient, and like we'd rather send it back and then have the operator reject it rather than miss it completely, even though it might have been a very hardly visible artifact. So there's some more robustness in the artifact detection.
Right. So like those two main things are basically, a much more robust artifact detection would be something required for autonomous, and I guess work put into making decisions about what area to go down. And
also in a decentralized way, because the robots might not have connection back to the base station, but might have among each other when they're deep inside the cave. So not only coordination, but also decentralized coordination.
And then a second question, that robot that lost connection.
Yeah.
Could you elaborate on why that was the case, and did that robot try and regain connection after it lost connection?
It did, yeah. So it was actually in its homing mode. It was trying to get back to the start, but there were dynamic obstacles, of course. So they basically shut off one tunnel branch, and then once that tunnel branch was shut off, there was no way in the map, or the robot did not see any way to go back to the base station from the map that it has built. So it would have had basically to explore further until it basically closed the loop and was able to go back. But that would have required a command from the operator, which unfortunately we're not able to get.
Right. So in hindsight, I guess for future work, you might implement some sort of way for it to explore, and I guess when it identifies that it's lost, I guess hit that switch for itself. So
so there was actually a pretty elaborate behavior tree that coordinated all the components in the robot in terms of what do you to do when you use Wi-Fi, how long to explore, all those kind of things. And you can always spin that further and make it more robust, but then also it adds complexity.
I have some questions. So at which point during exploration do you deploy the quadrotor?
During the finals, the quadrotor did not enter the course, unfortunately. We did try to. It took off in the staging area, but unfortunately it was not able to enter during the finals. We did test it afterwards. We had the testing day after the competition, where we fixed the bug that caused the robot not to enter, and then it was able to explore the cave environment. And that's the video you saw earlier. But unfortunately, during the finals, the quadrotor did not enter.
There was in the slides that was before the YOLO, so there was a video, and so a camera is looking at the robot, and I don't know if it's like a camera mounted on another robot or a camera on the quadrotor. It was not clear.
You mean this slide or
before?
Yeah.
Like, I don't remember. But so in some videos, so if you see the animal in the front of the car, so who is taking the video?
So in some of the videos that are here are just for illustration purposes and not from the competition itself. So we had a testing day afterwards, but we were able to follow the robot inside and we were able to take pictures. But only the onboard videos you see here are from the actual competition, or if they have this DARPA competition scoreboard on it, then they are from DARPA, but only available to us after the fact. So this is what DARPA recorded during, but was not available to us until after.
Ah, okay, so it's that type of work.
Exactly, yes.
And just curiosity, have you tried the quadropter inside the caves, narrow corridors?
We did, yes. So that's what I mentioned. So there was the opportunity to us to test inside this course afterwards. And then the collision.
So does it create dust that creates a problem for the robot?
It does create dust. However, it is not a big problem for the robot. So it has both LiDAR and vision board, and it does the visual thermal odometry as well. And the obscurance are not a big problem for the thermal odometry.
Thank you for the nice answers and thank our speaker again.